Hi, everyone. In this video, we want to examine limits of functions of several variables by looking at their behavior as we traverse paths in the domain. What we will see is that this provides us some sort of analog to what we saw about limits from the left and limits from the right in Math 5610. However, we will observe that for functions of several variables, things don't behave quite as simply as they did in that case, and therefore we will need to be careful about considering functions of several variables restricted to paths and what we can conclude about those limits and extrapolate to the full limit. So I really want to frame all of this today by looking primarily at two examples. Now, we are going to, in the video, work through all of these things sort of by hand, like computationally, algebraically, but I will also post some Desmos visualizations that will help you visualize the work that we are doing here. So let's start by considering this function. So f of xy is equal to x minus y over x plus y. Now, this function will be defined whenever y is not equal to negative x. Okay, so in particular, right, it's not defined here at this point, but we want to try and understand the limit nevertheless. Now, again, I'll give you some Desmos visualizations of this to play around with, but without looking at this particular function, right, let's just think generally about what we're doing here. Oops, that's not the positive y direction. This is the positive y direction. So you can imagine that I have, some function, of several variables. Okay, here's the surface that represents the graph of that function. Okay, and I want to understand, say, what's happening at some point. Okay, in my domain, call it A. Okay. Now, we know that the definition of the limit says, okay, well, you come up here, right? You sort of guess what you think your limit value ought to be, right? And then you need to, for every epsilon band around L, you need to find some delta ball in the domain so that all the values in that delta ball around A map to within epsilon of L. That's the formal definition. What we want to consider today is, well, what if instead of trying to do all that, what if I just restricted myself to some path? So this is a path. I'm going to draw sort of a curve here. Let me call it. So I'm imagining this curve lies in the plane here, in the XY plane in my domain, but it's going to A. Okay. And so I'll call that curve gamma. And the idea is going to be, well, what if I just looked at my function here, but restricted it to this curve and looked at what the values of this thing did and looked to see if they were approaching L. So to make this a little more concrete, let's take this and let's look at a particular example. So what if I just considered the path y is equal to x? Okay. Now, if I'm interested in the limit as x goes to 0, 0, I need to make sure that this is a path that passes through 0, 0. Otherwise, I'm not, like, back to this picture, if I was just looking at some path, over here that never passed through the point A, that wouldn't tell me anything. Okay. So I need to try and look through this path. I need to look at paths that go through 0, 0 in this case. Okay. And y is equal to x is a nice, simple, convenient one. Okay. So let's see what happens. Well, the nice thing about doing this is algebraically, it's going to reduce my number of variables, right? So if I consider this path, then really, if I go to look at f of xy, well, I'm taking y as equal to x, so I'm really looking at f of xx. So if I come up here, right, now I'm going to plug in x everywhere I see y. It's going to be 0 over 2x, which is just 0. So what we're seeing is all along here, for every x value except for x is equal to 0, because this function won't be defined when x and y are both equal to 0. But along this path, f of xx is equal to 0 for all x not equal to 0. So if I then go and look at the limit as x goes to 0, because as x goes to 0, that's taking me to this point 0, 0 that I'm interested in the limit at. So f of xx is just going to be the limit as x goes to 0 of 0. And so I get 0. Okay. Now, I might wonder then, what does that mean the limit? Maybe this limit then has to be 0. All right. Well, let's look along a slightly different path. Okay. So what if I consider the path? Let's choose another line, right? Like y is equal to 2x. Okay. Well, what happens then? Well, we'd have f of x. Now my y is going to be 2x. So now my function is going to look like x minus 2x over x plus 2x. So this is going to be what? Negative 1 over 3. Or sorry, negative 1x over 3x. Then I can cancel the x's, so I get negative 1 over 3. And that holds for all x not equal to 0. So again, I want to approach the point 0, 0, so that means my x better be going to 0. This is going to be a limit as x goes to 0 of just the constant minus 1/3, so I'll just get minus 1/3. All right, so now what are we seeing here? We're seeing that as you approach this point 0, 0 in the domain space, right, your function is actually approaching different values. And this might sort of be sounding familiar, right? It sort of sounds like, oh, you have a limit from the left and a limit from the right that are different from one another. And in a lot of ways, that's a good way to think about it, right? I have a limit along one path, which is giving me 0, a limit along another path, which is giving me a different value, minus 1/3. Probably my limit doesn't exist. And that's exactly correct. Visually, if I just think about what's happening in the domain space, right? What's happening is if I approach along this line y is equal to x, right? Along this line, all of my function values are 0. Okay. Along this other line, 2x, okay, all of my function values are negative 1/3. Now, remember that the definition of the limit really says that what I ought to be doing is I ought to be looking for some delta around the point 0, 0, so that all of my function values within this delta ball are within epsilon of some limit value. Well, the problem here is no matter how small you make this delta ball, you've got some function values that are 0, you've got some function values that are negative 1/3. So no matter what you try to make the limit value be, there are going to be some values in your delta ball that are arbitrarily far away from that. Well, not arbitrarily far away from that, but aren't arbitrarily close to that value. So if you try to make the limit 0, the problem is you'll never be able to find a delta ball small enough that all of your values, say, are within 1/4 of 0. Why? Because no matter how small this ball is, there are some points on this orange line where your function value is negative 1/3, which is more than 1/4 away from 0. Okay. It actually turns out that this is even worse. If you look along the path y is equal to mx, you will actually find that along y is equal to mx, the limit as x goes to 0 of f of x mx is actually equal to 1 minus m over 1 plus m. So this takes on many, many different values along different linear paths as you approach the origin. Okay, so One thing that we can see here is that there's some things going on here by looking along paths. Certainly, if we look along different paths and we get different values, then that ought to tell me that my limit doesn't exist, right? I'm going to be able to play this sort of game anytime my limit along different paths gives me different values. Now, there's an immediate sort of follow-up question, which is, well, okay, when I was just looking at functions from R to R, right, I also sort of had a converse that said, so if the limit from the left and the limit from the right were different, then the limit did not exist, right? So we sort of already see an analog to that just by looking at this example, okay? Now, again, you'd need to write it out slightly more generally to prove it, but roughly we already have the idea that that should be true. But then for functions from R to R, the converse is true, right? If the limit from the left and the limit from the right are equal, then the full limit exists, and you know the value of the full limit. So we start to wonder, well, what could I say? Maybe I could say something, like that. Okay, so let's look at another example. So let me take the function f of x is equal to y to the x. Now, I want to eventually look at the limit as xy approaches 0, 0. But let me make a comment first. This function, if x and y are both positive, this function is well defined. When x and y, when you start to allow negative values of either of them, things take a sort of a strange turn. Okay. So like if x is -1 and y is 1/2, right? Now all of a sudden there's a definitional question here, right? Like that's not going to give you a real value back. But if x is -1, or sorry, if y is -1 and x is 1/3, you will. So we're just going to deal with positive x and y values. Okay. Now 0, 0 is in fact an accumulation point of the domain of this function. Okay, so there's no issue. The limit is, we can talk about the limit. We're really just going to examine paths in the positive quadrant of the domain, so where x and y are both positive. Okay, so the first thing we might do is we might think, well, let's look along linear paths. Okay, so let's consider the path y. And I'm just going to take this to be y is equal to mx. And because we want to stay in that positive quadrant, let's just leave m should be positive. Okay. So let's look at this function along this path. So f of xy, well, that's going to be f of x comma mx, right? And that's going to be mx to the x power. So I can write this as m to the x times x to the x. All right. Now I want to know what's the limit. Now, again, I want to stay in the positive quadrant, so I'm going to look at the limit as x approaches 0 from above of m times x to the x. Well, the limit as x approaches 0 of m to the x, m is strictly positive. So any positive number to the x power, that's a power function, which is continuous. You just plug in 0. Any positive number to the 0 power is just 1. Okay. Now, the second piece is a bit different because you have the variable in the base and the exponent. I'll actually remind you that you may have seen in a calculus course, if you want to calculate something like this, okay, often one way we do this is we say, well, what if it did exist and was equal to L? Now let me take a natural log of both sides. So I should point out that this works because natural log is sorry, words are failing me right now, because natural log is continuous on its domain. So we get this. And now we can use properties of the log function. So log of a to the b is b times log of a. So this is really the limit as x goes to 0 of x times natural log of x. Now, if you try to apply this here, you'll get this goes to 0 and this goes to minus infinity. So you actually have to use L'Hopital's rule. The idea is this is going to 0 much faster than this is going to negative infinity. So that wins out and this goes to 0, but it's actually usually you use L'Hopital's rule. So then you say, well, wait, I wanted L. What I know is natural log of L is 0. That means that this limit must have been 1. All right, so this limit is 1. And so along every linear path, right? Because I've worked this out here for every linear path. Along every linear path, this gives me 1. Okay. Now let's look along some other paths. Okay. So what if we actually change this just ever so slightly? What if we put a power here where n was a natural number? So you can start to think about now, what if I added in this exponent here? So I was looking along paths that look like some constant times x squared or some constant times x cubed or x to the 4th. Like, so I'm sort of looking along all monomial paths now. Okay, what would happen then? Well, let's see. What's going to change here, right? And maybe I'll just keep track of this in orange here. I'm going to n here. I'm going to get an n here. I'm going to get an n here. I'll have an n here. Now, what happens when I need to look now at the limit as x goes to 0 from above of x to the nx? So let's see, I get an n there, put an n here, put an n here. But the whole thing is this goes to 0, so multiplying by a constant isn't going to change that. So yeah, I'm still going to get 1. So what we actually see is that not just is the limit 0 along every linear path going to the origin, it's 0 along all the monomial paths going to the origin. Okay. So you might start to wonder, like, well, wow, that's a lot of paths with limits going to 0. Maybe the limit as x, y goes to 0, 0 of this function is 0. Well, you can start to see, I've been a little bit dishonest here because I've been requiring that m be strictly greater than 0. What if m was equal to 0? If m was equal to 0, that's actually just looking along the path y is equal to 0. So if we look along the path y is equal to 0, what's going to happen? I'm going to get f of x 0, which is 0 to the x, which is actually equal to 0 for all non-zero x. Okay, and so that limit, in fact, is going to be 0, right? So I've been a little bit dishonest that all of these are 1, because if I just look along this path, right, I'll get that the limit is going to be 0. And so you might be going, okay, well, I have limits along different paths. That's going to give me then that that the limit doesn't exist, which is right. Actually, I want you to see that this is maybe even a little worse than you think. Because if I make a particularly clever choice, right, of path, right, I can make things look even worse. Okay, because maybe you think it's just somehow along the axis that things mess up. So if I look along the paths, look, pages in my notes. So if I look along the path y is equal to e to the minus m over x, where again, I'm going to just assume m is greater than 0. And I say, okay, well, what's going on here? Well, first, let's make sure, right, as x goes to 0, this exponent is going to go to minus infinity. E to the something that's going to minus infinity goes to 0. So as x goes to 0, this path is taking us to 0, 0. Okay, so that's the first thing we need to check. Okay. Now what? Well, let's look at our function. So what is f of x comma, e to the minus m over x. Well, that's going to be e to the minus m over x to the x power. I'm going to multiply those together. This is just going to be e to the minus m, which is a constant as far as x and y are concerned, right? So here the limit as x goes to 0 of f of x e to the minus m over x is just going to be e to the minus m. It's going to be that constant value. So what you see is that actually there are these whole host of paths of the form e to the minus m over x, along which your function is constant but has different constant values. Okay, so here again in this example, the limit fails to exist because the limit along different paths is different. Now we still haven't quite answered the question of, well, is there ever a time where we could look at multiple paths and be able to say, well, because the limit along these paths is equal, the full limit must exist. And the answer to that is really that it's complicated. So it's complicated because the short answer and probably the best way to just think about it is that there's not a simple way of doing anything like that. So certainly, right, there's no finite collection of paths unless you just made some ridiculously restrictive assumptions about how your function f could behave. There's no finite collection of paths that would allow you to do that. It's possible to come up with results where you can look along some infinite collection of paths. Again, you need to know a little bit more about your function and how it behaves. But such types of theorems are possible, but again, require additional assumptions on f. Okay, so we really can't get any nice sort of example or any nice sort of theorem where you can say, oh, the limit along these paths is equal, therefore the full limit exists. All we can really get is this theorem. Now, this is what we were saying at sort of the beginning, but in a slightly different way. So what is this theorem saying? This theorem is saying if f is a function from some subset of Rn to Rm, and gamma is some path in Rn, so it's just maps from R into Rn, so it gives you a path in Rn, and I want that path to live entirely in the domain of f. Then if the full limit exists, and if that path is in fact approaching the point A where you're taking the limit at, then the limit along that path must be equal to the value of the full limit. So what we can recover is essentially a theorem like from when we had functions from R to R. If the full limit existed, then the limit from the left and the limit from the right had to exist and be equal to the full limit value. What we have here is a theorem that says if the full limit exists for a function of several variables, then the limit along any path must exist, and that limit must be equal to the full limit. However, for functions from Rn to Rm, we cannot recover the converse, which allows us to say, well, if the limit along some finite number of paths is equal to this value, then the full limit must exist. Now, the proof of this theorem is in fact very similar to a proof we looked at in 5610. And that was a theorem which essentially allowed us to say something about limits of compositions of functions. Okay, so you have in fact seen a proof that's I'm going to write out the proof momentarily, but you've seen a proof that looks like this before. So if it feels familiar, it's because in many ways it is. It's just using slightly different domain and range spaces. Okay, so the proof is actually fairly short. So unsurprisingly, let epsilon greater than 0 be given. Our goal is to show that this limit is equal to b. We get to assume each of these limits exists, right? So the first thing we're going to do, so our goal ought to be, if I look at this function, this takes as an input t, which is a real number, and spits out a vector, right? So t gets fed into gamma. gamma will give us out a vector in Rn, then gamma of t gets fed into F. This gives us back a vector in Rm. So our goal is going to be to show that we can make the norm of F of gamma of t minus b less than epsilon by choosing an appropriate delta. Okay, so let's let epsilon greater than 0 be given. Okay. Now I'm going to sort of, just for the sake of making the writing a little bit easier, I'm going to use each of these limits in their own way. And let me, I'm going to sort of mark each of them. So I'm going to call this first limit, I'll call this star. And let's see, this one might be a little brighter. There we go. Okay. So since that limit exists, so by star, there exists some delta, and I'm going to have a couple of deltas. So I'm going to call this one delta 1 greater than 0, such that, well, what? From this limit, I ought to be able to make f of x minus b as small as I would like. Whenever the inputs are close enough together. So whenever the norm of x minus a is between 0 and that delta 1. So delta 1 is telling me how close I need to get a vector in Rn to a. I need to get it within delta 1 in order to ensure that f of that x value minus b in norm is less than epsilon. Okay. Now, we also have this limit, which I now want to use. I'm going to very creatively call it double star. By double star, there exists, I want another delta. So there exists, I'm going to call this one, again creatively, delta 2. Such that now I should be able to make gamma of t as close as I want to a. But I don't want to make it within epsilon of each other. I want to make this, I want to make gamma of t within delta 1 of a. And I can make gamma of t within delta 1 of a whenever t is close enough to 0. So now notice we can finish this up pretty quickly. So what does this tell us? So what do we have? When t I'll write this correctly in a second, I promise. So whenever the absolute value of t is less than delta, well, when absolute or is less than delta 2, we have this. Okay. And now this gamma of t, right? Gamma of t is a vector in Rn. So this is a vector in Rn that is within delta 1 of a. And whenever I have a vector in Rn that's within delta 1 of a, f of that vector, f of that particular x, in this case, that particular x vector that's within delta 1 of a is called gamma of t. So f of gamma of t minus b has to be less than epsilon. But now what have we done? We've shown that when we get t close enough to 0, and when we get t, absolute value of t small enough, then f of gamma of t minus b in norm is less than epsilon. Well, that's exactly what it means for the limit as t goes to 0 of f of gamma of t to be equal to the vector b. All right. And that concludes the proof. So again, what this shows us is that for functions of several variables, if you know the full limit exists and is equal to some value b, then the limit along any path approaching that same point must also be equal to b. The contrapositive of that, which we often make use of, is if you have the limit along two paths that are both approaching a, and you get different values, then the full limit cannot exist. That is true. What we unfortunately can't easily say is, oh, well, if you look at the limit along a path and it exists, or the limit along a few paths and they exist and are equal, then your full limit must be equal to that value. That's a much more complicated situation that requires much more nuanced theorems than we want to get into at this point. Now, once we have a nice understanding of limits, we'll now be able to move on, observe a few quick properties of limits, and define continuity in a very similar way to the way we define continuity for functions from R to R. With all of those tools in hand, we will then begin to discuss the much more delicate question of differentiation of functions of several variables and what, if anything, we can learn from that.